Okay, in the last lecture I derived the intensity distribution in the Fraunhofer diffraction due to single slit, and we saw that by looking at the intensity distribution where we can get the primary maxima, secondary maxima and the minimas. Also in the last lecture I showed you the screenshot of a software where I showed you the curves where I have plotted for the different maxima points. But now in this video I would like to plot for you in Mathematica so that you can yourself plot that. Okay, so let us see that. We all know that the intensity distribution in Fraunhofer diffraction due to single slit is I is equal to A sine alpha by alpha whole square, where alpha is equal to pi e sine theta by lambda. E is the slit width and lambda is the wavelength of the source. So let us try to see. So this I have opened a new notebook in Mathematica, okay, and I will try to plot this. So I will plot. My distribution is sine alpha by alpha whole square. A I can always take as 1. Okay, so I will plot sine alpha. Always, in order to write some symbols, you can use escape, write alpha, escape. Okay, sine alpha by escape, alpha, escape. Okay, and then you can make this square to the power 2. Okay, and then I need to specify the range of alpha which I would like to plot. Alpha, comma, I would like to take minus 3 pi to 3 pi. Okay, also I would like to also in the few previous videos of the Mathematica I have told you that in order to, if we have 2-3 functions on the same graph, I can label them by using plot legend. Here I would like to label the axis. So for that I should write axis label. Okay, this is a new command which I would like to tell you all. Axis label, and then you need to specify what you would like to label on the x-axis and y-axis. So again it has to go in curly bracket. The first one I would like to label on x-axis. The first coordinate will be x, second one will be y. Escape alpha, comma, again I would like to plot sine alpha by this. You can copy from here. Okay, copy, paste. Okay, this, that's all. Let us try to run. Shift enter. Yeah, so we got a very nice curve which I have showed you by hand. We all know that we will get this kind of curve. So here you can see that this, I'll tell you. Here I would like to label something, so I will just use format, input, label. Okay, sorry, okay, this I don't want to make it a label. And just a sec. Okay, yeah, this I would like to make a label, so I'll just delete this. Yeah, so here what do I get in this graph? At alpha is equal to 0 we got a primary maxima, and also from the equation I is equal to a sine alpha by alpha whole square, we can see that at alpha is equal to m pi I will get minimas. These two information already I got from this curve. Okay, so here this is my primary maxima, minimas. Okay, then I told you all that in order to get, so for example I can write here primary maxima I will get at alpha is equal to 0, okay, and minima I will get at alpha is equal to m into pi. Okay, these two things we can see from here. Now I would like to plot secondary maximas. Here they are already there, but how do we get that points? As I discussed in my video lecture, that in order to get the secondary maximas, I need to find the maxima point of this equation. That I will get by differentiating this equation. And in order to see the detailed derivation, you can just refer to my previous video on diffraction. And then after differentiating, I got two equations. First, alpha is equal to 0, that is already I got maxima. Alpha is equal to m pi, minima. And also I got another equation, tan alpha is equal to alpha, where I get secondary maximas. Okay, so let us try to plot this. I will plot separately, but I will take the same scale. So you can just check that these maximas which I am getting, which are of much lesser height as primary maximas, I will get from this equation. So, okay, so I'll just give a heading so that it looks nice. Okay, secondary maxima I will get by 10 slash alpha is equal to alpha. Okay, you can always reduce the font size from here. For example, I would like to make it 24. Okay, so this is my primary maxima and secondary maxima. Now I would like to plot this. If you write in the same cell, then it will not work. So you need to click and make another cell. Plot tan alpha. So we'll try to plot both these equations. Okay, and we need the intersection point of these two equations. So basically these are two equations, y is equal to alpha, y is equal to tan alpha. So I will try to plot it separately. Tan alpha, comma. Okay, so you understand I'm taking two functions. Y is equal to alpha, y is equal to tan alpha. So these are two functions. I have to make a list and then enclosed in the curly brackets, comma. Okay, now I need to specify the range of alpha, comma. Again I would like to take minus 3 pi to 3 pi. Okay, also I would like to see, because there are two functions on the same graph, I would like them to label plot legends, expressions. Okay, and also that's all. So now let us run this shift enter. Okay, can you see here? This was my previous curve. See, I have drawn on the same scale. At alpha is equal to 0, we got the intersection here, but this is a maxima. Okay, and another intersection. So basically this blue curve is a tan alpha curve, and this orange curve is the alpha, y is equal to alpha, straight line. The intersection point of these two curves, this will give me secondary maxima. I hope you can see that if you take a scale and you put it here, this peak is coming at the intersection point of these two curves. Another peak of this secondary maxima is coming on the intersection curve of this. And when you would like to see this point, it comes out to be 1.43 pi and 2.46 pi. Okay, you can just increase the scale of this and see this point. It is not exactly 1.5 pi, but it is little less than 1.5 pi. Okay, this is how you can see that where do we get the different maxima and minima points in the diffraction pattern, and you can plot and you can try to see. Okay, so this is what I would wanted to show you all. Also, what we can do, we can, if you want to see the intersection points, also I can plot, make it 10 alpha minus alpha. Okay, I have made it as one equation. Minus alpha, comma, alpha varies from minus 3 pi to 3 pi. Okay, sorry, 3 pi. Now if I want to plot this, okay, you see now, these were the two curves I have plotted separately, y is equal to x and y is equal to 10x. So 10 alpha is equal to alpha. And these intersection points, if I plot them together, this curve is modified. So basically this is the intersection point when the curve is cutting on the x-axis. So this is my intersection point. If you take a scale and you make a straight line from the first curve to the last curve, you'll see that these are your secondary maximas. Okay, so this is how you can plot yourself in this software and then see. Okay, thank you.